Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to talk on the module Piezoelectric, Inductive and Capacitive Transducer from the paper Electronics. So after completing this module, the students will be able to learn the following. First, the piezoelectric transducers, including the piezoelectric effect. Second, the circuit analysis of piezoelectric transducers and pressure sensors. Thirdly, the inductive transducer. Next, we will also discuss about the linear voltage differential transformer, Lvdt, its circuit will be analyzed. Next, we will also discuss about the eddy current transformer. And lastly, we will discuss about the capacitive transducer. So students, let us start with a basic introduction about the module. Piezoelectric sensors, they are versatile tool for the measurement of various processes. They are used for quality assurance, processes control, and for research and development in many industries. They have been successfully used in various applications such as in medical, aerospace, nuclear instrumentation, and in various sensors to consumer electronics or a pressure sensor in the touch pads of mobile phones. In the automotive industry, piezoelectric elements, they are used to monitor the contribution when developing the internal contribution engines. So the sensors are either directly mounted into the additional holes into the cylinder head, or the spark glow plug is equipped with a built-in miniaturized piezoelectric sensor. So the capacitive transducer is used extensively for the measurement of displacement, pressure, etc. The capacitive transducer or a sensor is nothing but the capacitor with variable capacitance. So it comprises of two parallel metallic plates that are separated by the material such as air, which is called as the dielectric material. So in the typical capacitor, the distance between the two plates is fixed, but in variable capacitor transducer, the distance between the two plates is variable. Next, we discuss about the inductive capacitor, where the inductance of a coil can be changed either by changing its physical dimension or by changing the effective permeability of the magnetic core. So in transducers using inductive elements, we normally use the second principle. The effective permeability can be changed by moving a core when is having a permeability higher than the air through the coil. But the discharge with the basic type of inductive transducer is that the inductance of the coil is neither related linearly to the displacement of the coil. That is, a large displacement occur accidentally. It is to avoid the disturbing the disadvantage that we use the Lvdt. So the existing inductive transducer have a relatively small output power and often require amplification of their outputs. Piezoelectric transducer. Piezoelectric transducers uses the piezoelectric effect for the measurement of pressure. So let us now discuss about the piezoelectricity. There are certain materials which produces an EMF when deformed by an application of pressure along the specific axis. This phenomenon is called as piezoelectricity or piezoelectric effect. This effect is widely used for the measurement of pressure. Piezoelectric crystal should have a charge asymmetry, that is, the center of the positive charge of the crystal does not coincide with the center of its negative charge. So there are two types of piezoelectric materials. First is natural single crystal such as quartz and tourmaline. Second is a synthetic polycrystalline ceramic such as barium titanate and lead zirconate. So let us now discuss about the piezoelectric effect. Piezoelectric effect is direction sensitive, which means tensile and compressive forces produces voltages of opposite polarity. So the magnitude of the generated surface charge Q is proportional to the applied force F. That is, Q is equal to D multiplied by F Coulomb, where the proportionality constant D is called as the charge sensitivity of the crystal. The capacitance of the crystal of thickness T and plate area A can be written as C is equal to epsilon R epsilon naught A by T. Therefore, the resulting voltage E naught is given by E naught is Q by C, which is equal to D multiplied by F multiplied by T divided by epsilon R epsilon naught A, which is equal to G multiplied by P multiplied by T, where P is the applied pressure and G is given by G is equal to D by epsilon R epsilon naught. G is called as the voltage sensitivity of the crystal, and from equation 1 we can write G equal to E naught by Pt, which is equal to E naught by T divided by P, where E naught by T is the electric field strength measured in volt per meter, which means G measures the electric field strength per unit pressure, which is expressed in volt meter per Newton. So from equation 2, we find out that G equal to epsilon R epsilon naught G, that is Coulomb per Newton. So from equation 2, it can be written as P equal to E naught by T divided by G. This shows that we can find out the value of the pressure once the value of G is known and that of E naught is measured. So let us now discuss the circuit analysis of piezoelectric transducer. Piezoelectric transducer PZT, which is a charge generator, can be thought of as a capacitor with a leakage resistor represented by Cp. So in order to measure the voltage, this circuit needs to be connected to an op-amp with either a capacitor at the input or in the feedback path. So the connecting cables introduce some stray capacitance to the circuit. So students, this figure shows the equivalent circuit of piezoelectric transducer installation. And this circuit can be replaced by its reduced form, where R equivalent equal to Rp parallel to R AMP and C equivalent is equal to Cp plus C cable plus C AMP. The input-output relation in the frequency domain can be written as E naught j omega equal to R equivalent divided by R equivalent plus 1 by j omega C equivalent multiplied by EI j omega. So this implies E naught j omega equal to j omega R equivalent C equivalent divided by j omega C equivalent R equivalent plus 1, this whole multiplied by EI j omega. So E naught j omega is equal to j omega tau divided by j omega tau plus 1 multiplied by ei g omega, where tau is R equivalent, C equivalent. Now the input voltage ei generated by the PZT can be written as ei equal to Q by C equivalent equal to D multiplied by F divided by C equivalent equal to dkx divided by C equivalent, where k is the force constant. So combining the above equations, we get E naught j omega by x j omega equal to kd by C equivalent multiplied by j omega tau divided by j omega tau plus 1. This is equal to kd by C equivalent multiplied by 1 by root of 1 plus 1 by omega tau the whole square multiplied by angle phi, where phi is pi by 2 minus tan inverse of omega tau. So from this equation, we get E naught j omega by F equal to D by C equivalent multiplied by 1 by root of 1 plus 1 by omega tau the whole square divided by angle phi. So we have the two cases. The first one is for omega tau equal to 0, we have E naught equal to 0. That is for a static pressure. And the transducer produces no steady voltage. For omega tau tending to infinity, E naught by F equal to D by C equivalent, phi equal to 0 degree. The response is independent of frequency but dependent on C equivalent at high frequencies. Let us now discuss about a piezoelectric pressure sensor. First, we will discuss about the electrostatic PZT, piezoelectric transducer. So the charge which is developed across a piezoelectric crystal, it is proportional to the force applied on it, and therefore it can be used to measure the pressure, which is nothing but force per unit area. It is mainly used for dynamic pressure measurements. They are small and rugged. The pressure can be applied in the longitudinal or transverse direction, and a high output is observed that is proportional to the generated pressure. Next is a piezoresistive PZT. They are based on the principle of the measurement of resistivity of silicon. Now here 4 pairs of silicon resistors, they are bonded onto a diaphragm. They can be used to measure static pressure also. Next type of piezoelectric transducer is a resonant PZT. They utilize the variation of resonant frequency of PZT crystals when a force is applied to them to measure the static pressure. The sensor, which can be in the form of a suspended beam, can be made to oscillate through inverse piezoelectric effect by applying an oscillating electric field. Let us now discuss about the advantages and disadvantages of PZTs. First, the advantages. They have a small size, lightweight and rugged. The electrostatic transducer may cover a dynamic range, pressure range of 1 to 10 to the power 5 and frequency range from 2 Hz to 1 MHz with almost no phase shift. Outputs are quite large. Special units operate up to 350 degrees Celsius. Now it comes with certain disadvantages also. That is, the electrostatic type cannot measure the static or absolute pressure for more than a few seconds. Second one is that all types are sensitive to temperature changes and therefore require proper temperature compensation. So students, let us now discuss about the inductive transducer. Inductive transducers are those in which the self-inductance of the coil or the mutual inductance of a pair of coil is altered due to the variation in the value of quantity under measurement. So there are three types of inductive transducer. First is variable reluctance type, second mutual inductance type, and third is the eddy current type. Variation of reluctance. The self-inductance L of a coil can be written as L equal to N square by R, where R is small l by mu A, where N is the number of turns in the coil, R is the reluctance of the magnetic circuit, small l is the length of the magnetic path, capital A is the area of cross section of the magnetic path, and mu is the effective permeability of the medium in and around the coil. So R can be written as R equal to 1 by mu G, where G is A by L, where G is the geometric form factor. Thus, the variation in either mu or G varies the reluctance, which in turn varies the inductance. Mu and G varies due to the displacement of various parts of the magnetic circuit. So the resulting change in the inductance can be measured to find the displacement. Consider the magnetic circuit, which is composed of number 1, a semiconductor ring with an electrical winding working as an electromagnet, second an air gap, third a plate of magnetic material, which is shown in this figure A. So the magnetic circuit is shown by the dashed line as shown in this figure. Let mu m be the permeability of the magnetic material, mu p be the permeability of the material of the plate, mu naught is the permeability of the air gap between the magnet and the plate. Since the magnetic circuit consists of three components, so the total reluctance of the circuit is nothing but the sum of reluctances of the individual components. That is, R total equal to R magnet plus R gap plus R plate. Now we can write R magnet equal to L magnet by mu m A equal to pi R by mu m pi A square equal to R by mu m A square, where R is the radius of curvature of the semicircular ring, A is the radius of cross section of the ring, and we have the R gap, which is given by 2x by mu naught pi A square, because the magnetic flux area and the air gap is nearly the same as that of the cross section of the semicircular ring. And the R plate is given by 2R by mu P 2AD, which is equal to R by mu PAD. So assuming that the magnetic flux originating from the magnet passes through an area of 2AD of the plate. Therefore, from equations 4, 5 and 6, we get the R total equal to R by mu m A square plus 2x by mu naught pi A square plus R by mu PAD, which is equal to R by A multiplied by 1 by mu ma plus 1 by mu pd, the bracket close, plus 2x by mu naught pi A square. Or we can write R total equal to R naught plus kx, where R naught is R by A multiplied by 1 by mu ma plus 1 by mu pd is equal to reluctance of the zero air gap. Now here k is equal to 2 by mu naught pi A square. So students, the corresponding change in the self-inductance of the coil is given from equation 1, that is L equal to N square by R equal to N square by R naught plus Kx, which is equal to L naught by 1 plus alpha x, where L naught is N square by R naught, which is the inductance from zero air gap, and alpha is nothing but K by R naught. It may be seen from equation 8 that the self-inductance has a non-linear relationship with displacement of the plate x. This can be converted to a linear relation by a push-pull variable reluctance transducer in the AC bridge. Let us now discuss about the linear variable differential transformer LVDT. It is the most commonly used variable inductance transducer. It is an electromechanical device which is designed to produce an AC voltage output proportional to the relative displacement of a transformer and an iron core. So these figures shows us the basics of LVDT and the construction of LVDT, which consist of one primary winding and two secondary windings. Secondary windings are identical in respect of their number of turns and their placement on both the sides of the primary windings. So a sinusoidal voltage EI of amplitude 1 volt to 15 volt and frequency 50 Hz to 20 kHz can be used to excite the primary through 1 volt at 2 kHz to 10 kHz, which is common. So a movable core of high permeability produces signal proportional to its displacement by changing the mutual inductance between the coils. Nickel iron alloy slotted longitudinal to minimize the eddy current loss is normally used to construct the core. When the core is in the middle position, a sinusoidal voltage of equal amplitude appears across the two secondaries. And if the secondaries are connected in series composition, as in the normally the case, these voltages cancel each other in order to produce a null voltage, as shown in these figures. So students, with the displacement of the core on either side of the null, the combined voltage of the secondaries increases linearly, undergoing a 180-degree phase shift while passing through the null. So the output loses its linear relationship with the displacement beyond certain limits, and this property restricts the range of the LVDT. And normally the range is from plus minus 10 micron to plus minus 10 nanometer. Let us now discuss the circuit analysis of LVDT. A simple analysis of the circuit reveals that the amplitude linearly varies with the difference in mutual inductances. So when the secondary is open circuited, the equation from the primary can be written as IPRP plus LP dIP by dt equal to EI. So taking its Laplace transform, it yields SLP plus RP multiplied by IP equal to capital EI. Now here we can write IP to be equal to capital EI by SLP plus RP equal to EI by RP divided by tau P S plus 1, where tau P is LP by RP. Now if small es1 and small es2 are the voltages generated in the secondary coils owing to their mutual inductances of the coefficient M1 and M2. Equations for the secondaries and their Laplace transforms are Es1 equal to M1 dIP by dt, Es2 is M2 dIP by dt. Es1 is equal to SM1 IP and Es2, the capital Es2 equal to SM2 IP. So now if we take the difference E0, that is Es1 minus Es2, putting all the values of capital Es1 and capital Es2, we get m1 minus m2 multiplied by s divided by rp divided by tau ps plus 1 multiplied by et. Now taking et to the in the denominator, and the ratio will be equal to S m1 minus m2 by rp divided by tau ps plus 1. Now representing E naught j omega and Ei j omega equal to j omega m1 minus m2 divided by rp divided by 1 plus omega tau p square plus 1 multiplied by angle phi, where phi is pi by 2 minus tan inverse of omega tau p. So this expression preceding angle phi represents the amplitude ratio of the output and the input. Since this omega, rp and tau p and the input amplitude are constants for a given setup, so the amplitude of the output A naught can be written as A naught equal to K multiplied by M1 minus M2, where K is a constant. So the value M1 minus M2 keeps on increasing with the displacement of the core up to a certain point, and then it starts falling as the core moves past one of the secondaries. So for a good dynamic response of Lvdt, the excitation frequency must be much higher than the core movement frequencies. This is necessary for distinguishing them in the amplitude modulated output signal. So the thumb rule is to set maximum core minus the movement frequency divided by the excitation frequency equal to 1 by 10. Let us now discuss about the eddy current transducers. Eddy currents, they are generated in conducting plate if it is placed near a coil carrying alternating current. So now this figure shows the generation of eddy current which are flowing in the target produces a magnetic field of their own which opposes that produced by the coil. So as a result, the flux around the coil is reduced, that is mu is lowered, with a consequent reduction of the inductance of the coil. So this effect depends upon the distance between the target and the coil, because the nearer the targets to the coil, the higher the eddy current and lower the inductances and vice versa. So now two arrangements are common, where the first one shows the target is placed perpendicularly to the axis of the coil, and second one shows the target in the form of the coaxial cylinder running over the coil. Capacitive transducers. Capacitive transducers can directly sense a variety of things: motion, chemical composition, electric field, and indirectly pressure, acceleration, fluid level, and fluid composition. The technology is low cost and stable and uses simple conditioning circuits. So capacitive detectors can detect 10 to the power minus 8 meter displacement with good stability and high speed under wide environmental variations. The advantages of these are: first, the non-contacting measurements; secondly, they have high resolution; thirdly, they have a high frequency response. The disadvantages are: first, they have rather low range; secondly, the displacement versus the impedance characteristics, they are non-linear and temperature dependent. Though a balanced coil can compensate for the temperature effect, the non-linearity has to be appropriately taken care of. Third, works only on conductive materials with sufficient thickness, cannot be used for detecting the displacement of a non-conductive material or thin metal foils. Generally, the parallel plate capacitors are used as the transducers. So, according to this theory, the capacitance C of such a capacitor is given by C equal to epsilon A by X, where epsilon is the dielectric constant of the inverting medium in SI units, X is the distance between the plates in meters, A is the overlapping area of the plates in meters square. Therefore, a variable capacitance device can be constructed by affecting the variation in either X or A or epsilon as shown in this figure. So the change in X, that is, since capacitance varies inversely as X, the plot of C versus X is a rectangular hyperbola which is rather inconvenient for measurements. So here the sensitivity S is dC by dx, which is equal to some minus constant by x square, which means it is not constant. In fact, S decreases as x increases. That is dC by C equal to minus dx by x, which means that the changes in the percentage of C and X are equal for small changes. Linearization of the input-output relationship is usually achieved by resorting to three different techniques. That is by using a charge amplifier. As shown in this figure, we can be successfully utilized to convert the non-linear relationship between C and X. So with currents I and Ix, capacitors C and Cx and voltages Ei and E0 are shown in this figure. And we can relate it like this as 1 by Cx integral Ix dt equal to E0 and 1 by C integral I dt equal to Ei. So now because the op-amp has a virtual ground at the input, that is I equal to minus Ix, so we can write E0 is minus 1 by Cx integral I dt equal to minus C by Cx Ei, which is equal to minus C multiplied by x divided by epsilon A multiplied by Ei. So in this equation, since all the factors are constant, the output voltage varies linearly with displacement. Next is by measuring impedance. So the second way of linearization is to measure the impedance rather than the capacitance, because the impedance is given by Xc equal to 1 by 2 pi nu C equal to x by 2 pi nu C epsilon r epsilon naught A, where nu is the frequency of the exciting voltage. It is obvious from this equation that Xc versus X curve is linear. So the third technique is by having a differential arrangement to produce the linear transfer characteristic. That is, here we are considering a differential arrangement of the capacitors. So a 3-plate capacitor is used over here, keeping the end plate L and N and fixed, and allow the middle plate capital M to move. It can be shown that the voltage differential delta E linear relationship with the displacement modulus X to the movable plate capital M. So students, let us now summarize what we have learnt in this module. First, the piezoelectric transducers, including the piezoelectric effect, they were discussed in detail. Secondly, the circuit analysis of piezoelectric transducers and pressure sensor were discussed, that is how the piezoelectric transducers operates. Thirdly, described the inductive transducers in detail. Next, we discussed about the principle of operation of linear voltage differential transducer, transformer, Lvdt, and analyze its circuit. Next, we discussed about the eddy current transformer. Lastly, the advantages and disadvantages of capacitive transducer and its working principle was discussed in detail. Thank you.